Hello everyone, welcome to our first lesson. So today we're going to be talking about set basics. So specifically we're going to be talking about the different ways to write a set, some operations on sets, subsets and real numbers, and stuff like that. So let's get started. So a set is defined to be a collection of objects called elements or members. Okay, so we typically use capital letters to name sets and lowercase letters to name elements within a set. So for example, we have the set A, which is in capital letters, and then we have the braces surrounding the elements in the set A. So we have lowercase a, b, and c as the elements, or you can also say members, in set A. And the elements in the sets are separated by a comma, as you can see here. So another set would be set K, which includes these four different names as the elements. So typically we use this symbol to denote is an element of. So for example, we would say, so this means that A is an element of capital A. Okay, so that's what this symbol means. It just means is an element of. So another example would be, so this set would mean that Mary and Kendall are elements of the set K. Okay, so I think that should be pretty straightforward. And then we will use this symbol, so it's basically that but with a line across it. So we will use this symbol to denote is not an element of. So for example, if this is given, then that means that G is not an element of set A. Okay? So another thing that I kind of forgot to mention before is that the order does not matter within the elements of the same set. So you can write BAC, ABC, CAB, or in any order that you want. It does not matter. The different ways to write a set, so there are, I think, 4 different ways that we can do this. So the first way is by something called roster notation. So in roster notation, we write out the elements that belong to the set in a list. And we separate the elements using commas. And the list is enclosed in braces. So an example would be, so we have braces, and then so these would all belong to the same set. So in this set, we are listing all of the elements out that belong to this set. Okay, so that's roster notation, where we are writing out the elements in a list. Another example would be if we have a pattern like this. So this is also a set that contains all the multiples of 5, starting with 5. So in this set, you can clearly see the pattern that's going on. So we have 5, 10, 15, 20. So as you can see, the difference between two adjacent elements are always 5. So the ... means that this pattern will go on forever. So another example would be this, where all the numbers within the set are multiples of 2. So we're starting with 2 and we're ending with 100. So this set does not go on infinitely. Unlike this one, it actually ends at 100. So this set basically means all of the even numbers from 2 to 100. Okay, so next we're going to talk about description notation. So that's where we place set braces surrounding a written description of the elements that belong to the set. So an example would be all students in 10th grade at your school. So this is describing the elements that are supposed to be included in the set. So if we write this in roster notation, it would be a list of all of the students' names in 10th grade at your school. It would be a list. But this is a description because this is a shorter and more convenient way to include all the elements but still not have to write them all out. So the third way that we can write a set is using set builder notations. So this method allows us to use formulas and describe more complicated sets of elements. So here is the basic layout of a set builder notation. So we have variable or formula describing elements in set. And then after this vertical line are going to be additional requirements or further description that the elements in the set has to meet. We can actually treat this as so that. Okay, so if we read this and we substitute this line for so what, we will get 2k so that k is a natural number. So the things that would go into this set has to fit the description of 2k, so it should be an even number, and it should at the same time be a natural number. And if you don't know what a natural number is, it's basically the positive whole numbers excluding zeros. So it'll be like, oh, it's supposed to go on. So it'll be those numbers. Okay, so this set will actually include not 0 because that's not a natural number, so we'll start from 2 because all natural numbers are supposed to be positive, and then we'll go 4, 6, 8, 10, ... because it doesn't say that there is a limit. So this is the actual set that belongs to this, okay? So let's look at another example. We have 5m plus 1. We can read this as so that. So we're going to say 5m plus 1 so that m is a natural number and m is less than or equal to 20. So we have two conditions here. The first condition is that n has to be a natural number, and the second condition is that it has to be less than or equal to 20. And it has to be 5m plus 1 when you write it out like the element. So when we write the element, so we're going to start with 1 because that is the smallest natural number and it is less than 20. So if we plug this in here, we get 6. Okay, so that's what we're going to do. So we have 6 as our first element, and then we're just going to plug in 2 here. So that'll be 11, and then if you continue with this pattern, you'll get 16, 21. But since there are actually a lot of elements in this set, and there's also a pattern, we're going to do ... and just go straight to the last element in the set. So since m should be less than or equal to 20, the biggest that m can be will be 20. So if we plug it in, you should get 101 for the last element. Moving on to the second page, so we're going to skip interval notation because it's basically just using inequalities but in notation form. So I don't think we need to go too much into that. So now we're going to take a look at the subsets of the real numbers. So first of all, we have the empty set, which is a set that contains no elements. Okay, so it can be written in symbol form as this, which is basically a set with nothing in it, or you can write this. So both of these mean the same thing, but you cannot write both. So if you write this is not an empty set. It is not empty. So if you write like this, this will be treated as an element. Okay, so when you're writing an empty set, you either write this or that, not both. Okay, so then we have natural numbers, which is denoted in a darkened capital N, and that is just all of the positive non-zero whole numbers. Okay, and then whole numbers are just natural numbers, but it includes 0. That's the only difference between natural and whole numbers, and you just write whole numbers when you're writing it in like set form. Then we have integers, which are denoted in the symbol Z, capital Z, and darkened. So integers are basically whole numbers, but including the negative side of it as well as the positive side. So that's integers. So rational numbers are denoted in the capital darkened Q, and they're just real numbers whose decimal equivalent either terminates or repeats. So this is like a description notation, as you can see, and it can also be described in the set builder notation form. So we have a fraction where the denominator and the numerator all belong to the integer, and also b is not equal to 0 because if it were, then the fraction would be undefined. Okay, so irrational numbers are just real numbers whose decimal equivalent neither terminate or nor repeat. So it's basically everything that is not rational number. So it's either going to be rational or irrational. And both of these are the two big categories that belong to real numbers. So real numbers are denoted in the capital darkened R, and real numbers are just all numbers on the real number line. So if you take a look at this diagram right here, basically everything are going to belong to the real numbers, and that include rational numbers and irrational numbers. So irrational numbers would include mathematical symbols like pi, the e symbol, also square roots that cannot be simplified down to a whole number, because those will have decimal that neither terminate nor repeat, like this one. And then we have irrational numbers, and in rational numbers we have integers, whole numbers, and natural numbers. And natural numbers are kind of like the smallest category you can get to. So now we're going to move on. So if you take a look at this diagram right here, basically everything are going to belong to the real numbers, and that include rational numbers and irrational numbers. So irrational numbers would include mathematical symbols like pi, the e symbol, also square roots that cannot be simplified down to a whole number, because those will have decimal that neither terminate nor repeat, like this one. And then we have irrational numbers, and in rational numbers we have integers, whole numbers, and natural numbers. And natural numbers are kind of like the smallest category you can get to. So now we're going to move on. Now we're going to move on to talk about set relations or relationships between different sets. So we're going to use these three separate individual sets for the following explanations. So first of all, we have set equality. So that's where two sets are equal, and they're equal if they contain the exact same elements. And remember that order does not matter. So the notation would just be set A. You don't have to write set A, you can just write A equals B. And remember, set names are supposed to be, usually they're supposed to be in capital letters. So an example would be maybe a set that contains numbers 1, 2, and 3 would be equal to a set that contains numbers 3, 1, and 2. Okay, so that would be an example of set equality. So we say that set A is a subset of set B if every element in A also belongs to B, and it is okay if A equals B. So if the two sets are equal, it is also a subset, and we're going to use this symbol. So this is the notation that you're supposed to use. So if you look at this example right here, so this is a set, and that is also a set, because when we're talking about subsets, we're saying that set A is a subset of set B. So in order for you to use this symbol, first of all, both of these have to be sets. So we're going to look at the number or the element inside of the set brackets and see if this number is included in the set right here. So you probably know that this means every number in between 1 and 2, including 1 and 2, and since 1 is a part of this, then we say that this is actually, this actually works, okay? But if you have, let's say if you have just 1, so we see that this is still a set, but this, without the brackets here, is considered to be an element, okay? So if it is an element, then you might remember from the notes before that we actually use this symbol to denote that something is an element of something else, like this. Okay, so this is an element, and this is a set. So it's basically the same thing here. So if you have an element on the left side, then we have to use this symbol and not that one. So you only use that symbol when you're talking about sets versus sets, but if you're talking about elements, then you have to use this. So a proper subset is if every element of A is also in B, but A cannot be equal to B, unlike a subset where it is okay for A to be equal to B. So that means that B has to have at least one more element than A. So this is the notation. We can actually treat it like this, where B has to be bigger than A. So an example would be this. So if we look at this set versus this set, so we're going to compare the elements in these sets. So we have 1 and 2, but we see that the elements in this set is also 1 and 2. So since these two are equal, it is not a proper subset. Because remember, B has to have at least one more element than A in order for it to be a proper subset. So if we change it to this symbol, then it will work, because in a subset, A can be equal to B. So then we have natural numbers, and the symbol, a capital darkened N, is a proper subset of whole numbers, which is true because whole numbers are, remember they're 0, 1, 2, 3, 4, ... and then natural numbers are just without the 0. So this set has one more element than this set does, so that is why it is a proper subset. And then lastly, we have this set, which is everything in between 1 and 2, but excluding 1 and 2. And then this set, which is only 1 and 2. So since A, the A set, or the set on the left, is way bigger, contains way more elements than the set on the right, it is not a proper subset. Okay? So the universal set denoted in U is the set that contains all the elements that exist within the realm of the problem. So usually it is the set of real numbers, which means it is like everything, but it not necessarily be that. So the universal set within the problem might just be restricted to high school athletes. So a set complement is, for a set A, the complement of A is the set that contains all the elements that belong to the universal set that do not also belong to A. So if this whole thing is the universal set, then within this set, if this is set A, then this area will be the complement of set A, which will be denoted in this symbol, like this. So this area So basically everything in the universal set that's not part of set A will be the complement of set A. So if we have high school athletes as set A, then the complement of that will be high school non-athletes. So an intersection of set A with set B is the set that contains only the elements found in both A and B. So if we look at this diagram, it'll be this area right here. And the notation will be A and then like a lowercase n kind of, and then followed by B. So if we look at these two sets right here, we'll see that they share no element in common. So the answer will be the empty set, which means nothing. Okay? So the union of set A with set 2 is the set that contains the elements found in A or B or both. So on this diagram, it'll be everything that's in A and in B. So when you write the notation, it'll be A and then a kind of lowercase u and then B. So that is the notation, and an example will be, so for this, this set right here and this set right here combined to make this set, which is everything that's included in this and that set, but without repeating any numbers. Okay, so there should be no repetition in the final set. And another example would be the set n, which is natural numbers, and the set that contains the element 0, which makes the whole number, because remember, natural numbers are basically whole numbers without 0. So this is another example. Last but not least, we have set subtraction. So the set denoted by this is the set that contains all the elements contained in set A that do not belong to set B. So for this diagram, it'll be this area. So everything in A that do not belong to set B, which is excluding the shared area. So this is the notation, which basically means A without B. So an example will be natural numbers denoted in capital N without the set, the series of numbers from negative infinity all the way to 1.5. So the result will be, we're going to start from 2 because n has to be a whole number. So we're just going to go 2, 3, 4 all the way to infinity because there is not a limit set. And then another example would be r, or real numbers, without the sets containing 0. So it'll just be negative infinity to 0 plus, remember this sign from the union. So this is the sign that we're going to use that means combining two sets. So here we're going to do this set combining with 0 to infinity, because that is basically everything on the real number line excluding 0, because we see the parentheses here indicate that 0 is not included. Okay, so that is the end of our notes for today, and I'll see you guys next time.